Hello. In this video, I'm going to go over section 11.1, functions of several variables. Now, this video will feel a little longer than it actually is because I will be reviewing things like domain and like graphs and stuff that you know from previous classes, but I feel it's worth reviewing so that this section makes more sense. Now, before I do that, let me tell you what's happening. Up until now, we looked at functions whose domain, right, the domain of our functions, it was always the real numbers. In other words, we had something going from the real numbers to the real numbers, so y equals f of x. And then for the past couple of sections, we looked at functions whose domain was the real numbers, but then the output or the range lived in R3 or maybe R2. So this is called a vector function. In vector function, so I have my parameter t, and then the output is a vector. Like in this case, in R3, I'm going to do x of t, y of t, z of t. Now, the domain is a scalar. It lives in R. So the graph is a curve, okay? And it could be a line, it could be a parabola, but it could also be a helix, or it could be something like go like that, whatever, okay? Now, what we're doing in chapter 11, and we're going to look at functions of several variables, my domain will live in R2, and then the output will live in the real numbers. Now, let me show you graphically what's going to happen. So this is x, this is y, this is z. Now my domain will live in R2. Okay, in this case, I'm doing XY plane. And imagine I have a source of heat here. And then at this location XY, at this point XY, I record the temperature and I get this much. Or and then I go here and I record the temperature. I go here, I record the temperature. Okay. So you end up getting, so let's say I'm here, right? So let's say, depending on what this looks like, okay? So let's say I record my temperature, I'm here, and then I record my temperature here, and I'm here, and then I record my temperature here, and I'm here, whatever. I end up getting something like if you were to look at the height, right? So I end up getting something that it's going to be, let me just draw it like this. It depends on the height, right? But you can imagine it'll look something like this. So you end up getting a surface, okay? Something like that, okay? So you end up getting a surface. Perfect, okay? So you end up getting, like, depending on what we have, you end up getting the boundary of this, okay? You end up getting the boundary. Okay, perfect. Now, since we're defining this new type of functions, like functions of several variables, we have to talk about the domain, the range. We're going to look at continuity and limits. We're going to talk about the derivative and stuff. Okay, so for the next couple of sections, we'll be learning how to deal with this new type of function. So let me start with the domain and the range. So the domain, before we do domain, let me actually define this as a function of several variables. Okay, so let me start by saying that a function of several variables, in this case, I'm taking two variables, but you could have a function of 10 variables, okay? But we're going to focus on functions of two variables. It's a rule that assigns to each ordered pair of real numbers, and we're going to use, this is my domain, x, y, in a set D, which is a subset, let me put it here in parentheses, it's a subset of R2, a unique real number denoted by my function evaluated on xy, and this is going to be equal to z, okay? Now, before Calc 3, we knew that if I had a function y equals f of x, like both the domain and the range live in the real numbers, this is just the largest subset of the real numbers that we can plug into f and get a real and defined number. And hopefully you remember what this means. Real means, uh, real means, like let's say no negatives in even roots. And then define means no division by zero. No division by zero. Now, in R3, now that we're dealing with functions of several variables, the idea of the domain will be exactly the same thing, but it'll be, instead of a subset of the real number, I'm going to say same, but domain, domain is now a subset of R2. Okay, perfect. And now the range is the set of outputs, so it'll be the set of outputs. So you can even write this as, well, it'll be the set of f of x, y's, right? Such that the point xy lives in this little domain, which is a subset, let me say, a subset of R2. Okay. The notation is f goes from R2 to R, fancy R, which is the same as saying, one more time, I take xy going to f of xy, which is equal to z. Okay, perfect. So literally, we were dealing, like, we know what y equals f of x is. Now y is also an independent variable, and we're calling z that output that comes from plugging x and y into the function f. Okay. So let's review the domain of some of these functions in 2D that we'll be using now in 3D. Let me start with the natural log of x. So we know that the graph of the natural log of x looks something like this, with a vertical asymptote at x equals 0. Therefore, the domain is going to be starting at 0 all the way to infinity. For arcsine, we know that arcsine is the inverse of sine. So we know that the function, let me say this is sine of x. So sine of x, we know that we have to restrict the domain from pi over 2 to pi over 2. And then the range goes from -1 to 1. And the graph will look something like, let's see, will look something like this, right? So the domain is restricted from -1 to 1, and then the range will go from -1 to 1. Now, when I talk about arcsine, then arcsine will be, well, literally the opposite, because it's the inverse function. We make this smaller, resize a lot smaller. So now if I look at arcsine, I know that it is the inverse of sine, so they will interchange the domain and the range. So now the graph will go from -1 to 1, that will be my domain, and then the range will go from negative pi over 2 to pi over 2, and this is a reflection, so it'll look something like, I mean, this is not going to be perfect, but it was something like this. Okay, perfect. So now the domain will be from -1 to 1. When it comes to root of x, then root of x, we know what it looks like. We know that it looks something like this. So this is root of x. And then the domain, I get to plug in 0. So I get from 0 to infinity. And then finally I have the graph of 1 over x, which hopefully we all know. It looks something like it looks something like this. Okay. So the domain is all real numbers except for 0, which we can write as infinity to 0, and then from 0 to infinity. Okay, perfection. Now let's look at other graphs, like for example, sketch the graph of the following functions. Well, first of all, if I have a circle of radius r centered at hk, then we know that the equation will be x minus h squared plus y minus k squared. It's equal to r squared, and the graph is just a circle. So let me assume that this is h and this is k. Then this is going to be the center, and then hopefully I get to, that's not too bad. So if that is my circle, and make sure that's the center, then we know that this will be the radius r. Okay. Now, if I have an ellipse of x radius a and y radius b, I just wanted to make it as easy as possible, right? This is going center at hk, then this is equal to x minus h squared divided by a squared plus, and then I have here y minus k squared divided by b squared is equal to 1, okay? Perfection. And then the graph of this will be equal to, so this is uh, So this is harder to see. Usually we center it at 0, 0. But imagine that if this is the point, this is h and this is k, and I draw my ellipse, and I draw an ellipse. So let's say it's something like this. Okay, it's not gonna look like an ellipse. So maybe I can move it a little. Oh, it's okay. Maybe if I come here. Oh, look at me killing it. All right, perfect. Then then this is going to be A, and this is going to be B. Okay, perfect. And you'll see in a second why I'm reviewing these things. Okay, let's do an example. So find and sketch the domain of f of xy equal to the natural log. So this is, we're not sketching the graph of the natural log of this, we're sketching the domain of it, okay? So let's see. What do we know? Let me just split this into what we know. And then let's see. And then a domain. So algebraically. And then we can look at the graph of the domain. Graph of the domain. Okay. So what do we know? Well, we know that the domain of the natural log is whatever it's inside the natural log has to be larger than 0. So let me just remind you what we just did. Natural log of x, right, is defined for x larger than 0. What does that mean in our case? Well, it means that we need whatever it's inside the natural log, which in this case is 16 minus x squared minus 16y squared. We need that to be larger than 0. That's what we need, okay? So now that sort of, it's starting to look like an ellipse, but let's see. So what I'm going to do is let me move the 16 to the other side, which is the same as just moving x squared minus 16y squared to the other side and flipping the sign. So I think I'm going to do that. So check this out. I get x squared plus 16y squared. So it's like I'm moving this to this side. It's less than 16. Okay. I divide everything by 16 and I get x squared divided by 16 plus y squared is less than 1. Okay, so that's what we need. So what does that mean? It means that the domain algebraically speaking, it's going to be the set of points x, y in R2, right? In R2 such that x squared divided by, I'm going to say 16 plus y squared is less than 1, okay? In other words, let me make sure that we understand this. It is the interior of an ellipse, okay, of an ellipse centered at 0, 0. And then I'm going to say the x radius is equal to 4, okay, the x radius at 0, 0. X radius is 4, and then the y radius, it's equal to 1. And then I know you know this, but just in case, don't forget that this little epsilon here means in. Okay, the little bar here means such that, and I mean, you know, this is less than. Okay, perfect. So I'm going to grab this, okay? I'm going to grab this. So let's see. Blue so I can underline this, and then black to make the axis. So my domain is just an ellipse. And then the major axis, which is what's actually called, goes from -4 to 4. And then the minor axis goes from -1 to 1. Now you have to be careful because since we have strictly less than here, strictly less than, we're not going to include the boundary. So it's like if I draw an ellipse, I have to be careful. I'm not including the boundary, okay? So I'm going to draw it like this so that you know that it means that I'm not including the boundary. So maybe I'll make it prettier and then make the boundary dashed so that you know that it does not include the boundary. Let's see if this is, see, that's much better. Okay, that looks better. And then I can make some changes here so that, let's say precision, so that I can get rid of, you know, oh wow, I was, okay, that's a lot, but you know, boop, 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 boop. Okay, maybe too much. Okay, like here, 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 and whatever. All right, perfect. So also now I'm going to include the interior. And I know there's a way to do this, but I don't remember. So I'm just going to do it old school. All right, perfect. So let me make sure that you understand it does not include the interior. So it does not include when x squared divided by 16 plus y squared is equal to 1, okay? Perfect. Okay, let's do another example. So find and sketch the domain of the function arcsine of x squared plus y squared minus 9, okay? And I'm going to do the same thing. I'm going to split this into 3, which what we know from previous knowledge, and then the actual algebraic domain, and then the graph, okay? Graph of domain. All right, so we have arcsine. So what do we know about arcsine? Arcsine goes the domain of arcsine. So arcsine of x is defined for x in between -1 and 1, including -1 and 1. Okay. Now, so what do we need? We need again, so we need whatever is inside arcsine to be in between -1 and 1. In other words, we need -1 to be less than or equal to, and then whatever it's inside. So x squared plus y squared minus 9 less than or equal to 1. And then you can add that 9 everywhere, and you get 9 minus 1 less than or equal to x squared plus y squared less than or equal to 1 plus 9, which gives me that a is less than or equal to x squared plus y squared, which is less than or equal to 10, okay? So algebraically speaking, my domain is going to be the set of all x, y's in R2 such that, let me write this as, so that it's really obvious. I'm going to say the square root of a squared is less than or equal to x squared plus y squared less than or equal to, and then the root of 10 squared, okay? So in other words, my domain is the area between the two circles, centered at 0, 0, with radius root of 8 and root of 10, and it includes the boundaries, okay? And includes the boundaries, okay? Because we have the equal signs, okay? We have the equal signs. All right, so let's see. Graphically speaking, I'm gonna do what I did before. So this is x, this is y. I'm gonna draw a little circle. Let me see. This is one circle. So this is one circle, okay? I'm gonna make that the one with radius root of 8, and then I have another circle. I'm gonna make that one the one with radius root of 10. So this is root of 8, this is root of 10, and then this is negative root of 8, and this is negative root of 10, and my domain is the area in between the two circles. Actually, hold on. This is going. Wait. Okay, maybe a little bit. No. Okay. Here we go. Boop doo. Boop doo. Look at that beauty. Okay. Oh no. What? You see that? Oh, because it was like one stroke, so I cannot. Okay, I have to have more control. That's pretty good. All right, perfect. Hold on, I'm not loving the fact. Precision. This right here, it's killing me. All right. Perfection. All right. All right. All right, so now let's look at the graphs of these functions. I have functions in 3D. The graph of a function in 3D is a surface. Let me make it blue. It is a surface in 3D. And you can think about it as the graph will be lying directly above or below the domain. So I'm here in 3D. Maybe let me draw it here, right? So if this is the domain, right, this is like the shadow, and then your actual function will be a surface here following whatever height the domain tells you to take, okay? Perfection. All right, so let's just review some of these graphs. I want to tell you what my plan of attack is when it comes to sketching the graphs of 3D functions. The first thing I do is I replace f of x, y with z so that now I'll see if this takes me to a known surface and I know the graph of the function. Is it a known surface? Meaning, do I get a plane? Do I get a sphere? Do I get something that I already know how to draw? Okay. So let's see, let's start with the first one. So we know that the equation of a plane with normal vector ABC containing the point 0, 0, 0 looks like AX plus BY plus CZ equal to 0. We know this from a couple of sections ago. Now, in this section, if I want you to graph a plane, I'm not going to give you the equation like this. I'm going to give you a function of x and y. So you could have something that looks, let's say, for example, I can give you something that looks like, oh, f of x, y, it's equal to, let's say, d minus ax minus by, right? Something that looks like, it sort of looks like a plane, but I don't think that until you replace f of x, y with z, and you end up with z plus ax plus by equals d, you don't realize that you're dealing with a plane. Okay, so now if this is the case, so now I'm just writing it like this so it's easier to visualize. If I give you a function that looks like it could be a plane, you replace f of x, y with z, then if you want to be able to sketch the graph, what you do is you find the intercept, okay? And you find them by saying, well, the x-intercept comes from letting y and z be equal to 0. If that's the case, then from here, what do we get? From here, we get that 0, z is equal to 0. And then you get d minus ax and then y is also equal to 0. So from here, you would get that ax is equal to d, therefore x is equal to d divided by a. So you get the point d divided by a, 0, 0. And then you can do the same with the other intersections, okay? But long story short, you find the intersections and you'll be able to sketch the graph of this plane by just doing your x, y, and z axis and then saying, well, this is my x-intercept, which is the point DA 0, 0, and then you find your y-intercept, then you find your z-intercept, and you know that they form a plane. Okay, something that could look like, contains those points. Sometimes the book likes to just draw a little triangle. That's fine. I'd rather draw it like an actual plane. Okay, but that's fine. Whatever makes more sense to you. So usually I just draw a little plane that goes through those points, something like this. Okay, so that you don't forget this is actually a plane. Okay, perfect. Now, when it comes to a sphere radius r center at 0, 0, 0, we know that the equation is, what is the equation of a sphere of radius r? It's a square plus y, I'm lying, it's x squared plus y squared plus z squared equal to r squared, okay? Then again, if we're looking at the equation of this 3D function, it's not going to be given in terms of z, right? You sort of have to replace f of x, y with z, and then notice that it's taking you to a sphere. So you could say something like, let's see, something like, let's say, let me go to, yeah. So you can say something like, oh, f of x, y, it's equal to r squared minus x squared minus y squared, and then I take the square root of that, okay? That's how you know, because when you go, oh, wait a second, this is z, and then you undo what I just did, then you get back to this and you realize that you're dealing with the equation of a sphere, okay? Now with a cylinder, I have both here, a cylinder and a paraboloid, because they look very similar, but they're not, okay? So you're not going to get a function in 3D that looks like a cylinder, because you know that the equation of this is x squared plus y squared equal to r squared, okay? And then in order for this to turn into a three-dimensional situation, you have to assume that z is free. And this is how you end up with, this is how you end up with, this is how you end up with a little cylinder, okay, of radius r. When you have all your circles at all the different heights, okay, so z could be anything, but this is still r. Okay, and I forgot to mention about this one right here. If I do this, I forgot to draw it, but if I do this, I'm only taking the positive one, so you have to be careful. This will be z, but z, it's positive, okay? So this is going to look like the upper half of a sphere radius r, center at 0, 0. So this will be something like this, just the top half, okay? All right, okay. So then this is going to be r, and so on. Okay. Now what's going to happen is if I replace that r with f of x, y, so if now I have x squared plus y squared equal to f of x, y, then this is going to be my z, okay? And then as you plug in, you end up getting something called a paraboloid, okay? So it's always positive, so your z, it's only above the xy plane. And then if you plug in 0, 0, you get the point 0, 0. And then again, it's like z is all the different, like, right, like if you plug in your values of z, you still get you still get some circles, okay? Or you can think about it like this is a parabola on the xz plane, and this will be a parabola on the yz plane, okay? So you end up getting something that looks like parabolas, and then it is actually a surface, is three-dimensional, so it looks something like that, okay? Perfect. So if you were to look at this from the xz plane, it looks like parabolas. If you look at it like yz plane, it also looks like parabolas. All right, that was just like a little review to make sure that what we're about to do now makes sense. So let's see. You want to sketch the graph of f of xy equal to 14 minus 4x minus 5y. So again, the very first step is to replace f of xy with z. So I'm just going to sort of turn it into steps. So step one, I'm going to say let f of xy be equal to z. And I feel like the moment you do that, then this immediately starts to look like something that you've seen before. So from here I get, right? I get that this is, I'm going to write it as 4x plus 5y plus z equals to 14. Hey, wait a second, this is a plane, okay? A plane, okay? That's why we reviewed this. And then my that could be actually my second step. Once I replace f of xy with z, I go, wait, do I know what this is? So step two, do I know what this is? Is this a known surface? And the answer is yes, it is a plane. Since it is a plane, then I already know how to sketch it. So my step three is just to graph it. So graph the plane, and we're going to do it, graph the plane. We're going to do it the way we did a minute ago by finding the x, y, and z intercepts, okay? So let's see. Intercepts. Okay, so let's see. X intercept happens when y it's equal to 0 and z it's also equal to 0. So from here I'm going to get that real quick. If I make this 2 equal to 0, then I get that x is equal to 14 divided by 4. So from here I get that x is equal to 14 divided by 4, which is the same as 7 divided by 2. That means that my x-intercept is the point 7 halves 0, 0. The y-intercept happens when x is equal to z equal to 0. Again, I go to my plane, I let x and z equal to 0, and I get that 5y is equal to 14. So that means that y is equal to 14 divided by 5, which gives me my y-intercept. So I get the point 0, my y-coordinate 14 divided by 5, and then 0. And then finally my z-intercept comes when x it's equal to y, it's equal to 0. I go back to my plane, I make x and y 0, that gives me z equals 14. So the intercept looks like 0, 0, 14, okay? Perfect. So then the graph is just This is x, this is y, this is z. I have my x, y, and z intercepts, so I get that this is the point 7/2, 0, 0. And this will be the point, this will be the point 0, 14 divided by 5, 0. And this is the point 0, 0, 14. And then again, you can connect them, like turn it into a little triangle. I don't love it like that. I like to actually draw a plane. Either way, this would be fine. So I'm going to go like this, right? And then like this, and then like this. Okay. Perfection. Okay. Sketch the graph of g of xy equals to the root of 9 minus x squared minus y squared. I like how I've been calling this functions just f because we usually use f for functions, but I can call it anything I want. Okay. So then again, step one. So step one, let g of xy be equal to z. So then I get that z is equal to root of 9 minus x squared minus y squared. We know that this is positive, okay? Don't forget that. I'm going to write it here. I'm going to say, I'm going to say this implies that z is positive. So z has to be larger or equal to 0. Let's see. Step 2, do I have a known? So step 2, known surface. Let's see. So I'm going to square both sides. So I get z squared is equal to 9 minus x squared minus y squared. From here, I get that x squared plus y squared plus z squared is equal to 9. The answer is yes. Okay. This is the equation of a sphere center at 0, 0, 0, radius 3, but we only take the top half. Okay. So let me write it. The answer is yes. Yes. This is sphere, radius 3, centered at 0, 0, 0, only top half for obvious reasons, right? Because z is not equal to 0. So let's sketch the graph. So step 3, I'll make this smaller maybe. So step 3, graph. Well, again, we know what it looks like. It's just the top half of a sphere, radius 3, center at 0, 0, 0. So this is x, this is y, this is z, this is 3, this is 3, this is 3. Okay? And then this looks something like this. And it's just the surface, okay? So it's like the boundary, not field, right? Okay. Something like that. Perfect. It's supposed to be a sphere, so maybe I need this to be like more round. Okay. What else do we have here? Level curves. Okay. So level curves are interesting because they are now curves. So I'm back to one dimension. So these are curves with equations f of xy equals to k, where k is a constant and in the range of f, okay? Now, real quick little note, a contour plot is the graph of multiple level curves. So the idea is like, let's see if this makes sense. The idea is like you're looking at this from the top. So imagine you have your three-dimensional graph. So imagine like the maps that you see, what are they called? When you see a map, the map of anywhere, right? It's a two-dimensional thing, but then you can look at the different colors, and depending on the colors, you know how high or how low the mountains are. Okay. So what we're gonna do is imagine I have a graph in 3D. So let's see. Imagine this is my graph, right? If I were to look at this on the XY plane, I would see circles. Like, so if I look at it from the top, right? Like imagine one more time, it's like I have this little bell-shaped surface. If I look at it on the XY plane, I will be seeing a bunch of little circles because it's like I take it and I push it down and I turn it into a two-dimensional thing. It collapses into a two-dimensional graph. Now, since these are going to be curves in 2D, right? Because I'm turning my three-dimensional surface into 2D by looking at it from the top, then I want to review some of these graphs. So, I mean, come on, we know this. So I'll go quick. So if I have y equals 2x, I know that I'm dealing with a line. So this is just a line. If I'm looking at y equals root of x, I already did this in this video, but this looks like that. If I'm looking at y equals x squared, then this is going to be equal to a parabola, right? It opens up because the coefficient is positive, and then x cubed will look something like this. Now, of course, I'm assuming that you remember from college algebra, pre-calculus, or any other math that how to transform these things, okay? What happens if I add a number? What happens if I multiply by a negative and so on? So let's start with draw a contour map of f of x, y equal to x squared plus y squared. Okay, so one more time, step one, what you're going to do is step one, these are the curves that you get when you let z be a constant, okay? So meaning what height do I get every single time I get that this is a constant? So this is going to be k, it's equal to x squared plus y squared. And then I'm going to ask you, you can make a table of values before you sketch that, okay? So step two, give values to k. Now, of course, I mean, I see this and I see that we have x squared plus y squared. So of course, the values that I'm going to give are going to be perfect squares so that I can think about this of circles of radius k, okay? So let's see. So k and then my x squared plus y squared, okay? So, I mean, I don't need to do this, but long story short, just like so that you see what I mean. So if I make this 1, it'll be x squared plus y squared equal to 1, or x squared plus y squared equal to 4, or x squared plus y squared equal to 9, or x squared plus y squared equal to 16, right? So say I asked you to draw 5 level curves. So then when k is equal to 25, I have x squared plus y squared equal to 25. So what's the graph of my level curves? Well, step three, graph, it's literally what they look like from on the XY plane, okay? On the XY plane. So let's see, this is 1 and this is 4 and this is 9 and this is 16 and this is 25 because I only asked for 5 level curves, and then this is -1 and -4 and -9 and -16 and -25. And maybe I should try to draw this like this. Let's see. So I have a circle here. Let me try one more time. Circle radius 1, and then a circle of radius 4, and then a circle. This is not going to be perfect. Of radius 9, especially that one. A circle of radius 9, and then a circle of radius 16, and then a circle of radius 25, okay? With that beauty, something like that, okay? Um, so let me see if I can make, hope you get the point. But what I actually want to talk, oh, this is beautiful. Can we make it perfect for y'all? Perfect. Look at that beauty. Look at that. That's perfect. Maybe this one a little bit. Okay. So long story short, there you go. That's it. Now, think about this. You're looking at this from the top. So the graph of this looks like it'll be smaller, right? Smaller the closer you get to 0. So this is the graph of a paraboloid, okay? So in 3D, this looks like, in 3D, this looks like this. So it looks like this. And then you keep changing the values of k. So then this would be, hold on, this is the level curve when k is equal to 1. So super small here, radius 1, right? Radius 1. Okay, radius 1. And this is when it is 4. And this is when it is 9. And this is when it is 16 and so on. Okay? Perfect. Example number 2, we have draw a contour map of f of xy equals to x cubed minus 3y. Again, we're not drawing the three-dimensional surface, we are drawing level curves. That's what a contour map is. So step 1, think about this like k is equal to x cubed minus 3y, okay, minus 3y. And then from here, in this case, it's easier to just turn this into something that we understand. For example, I would solve for y, okay? Right? So the previous one, I didn't solve for anything because it looked like a circle already. In this case, I'm not sure what this is. I'm going to solve for y. If I solve for y, I get 3y is equal to x cubed minus k. Divide by 3, you get that y is equal to x cubed divided by 3 minus k divided by 3. Okay? Now, my second step is, and then I'm sticking to 5. My second step is to replace k with 5 other numbers and then sketch them. Okay? Now, this one it's harder to visualize in 3D, so maybe I'll just show you. I'll record a short video on using Desmos to show you these things. Okay? So step 2, change the values of k. So change values of k. So let's see, what do we get? So I get that y is equal to x cubed divided by 3 minus, when k is equal to 0, I get that. So maybe I can say here, maybe make a little table. I like making tables. So k versus y equals x cubed divided by 3 minus k divided by 3. So k is equal to 0, I just get y equals x cubed minus 3. If I make k equals 1, then I get y is equal to x cubed divided by 3 minus 1/3. If k is equal to 2, I get that y is equal to x cubed divided by 3 minus 2/3. If it's equal to 3, maybe make this smaller. When it's equal to 3, I just get, I already have 3 of them, so let's do 2 more. If I make k equal to 3, I get y equals x cubed divided by 3 minus 1. And then if it's 4, I get y equals x cubed divided by 3 and then minus 4/3. But long story short, and this does not have to be perfect, it's just like the feeling of what the level curves look like. Then step 3, the graph, I'm going to say contour plot. This is going to be equal to, I have here, when k is equal to 0, I just get x cubed divided by 3, which is just a graph of x cubed, and then divided by 3, but it goes through the point 0, 0. So this is k equal to 0. Now, if I didn't add any negative numbers. I should have, but I didn't make k negative. So I'm always just moving this down by some units. So I'm going to copy paste this. So copy paste. So if I have here, it's like literally take the graph and move it down 1 unit. So this is going to be k equals, this is going to be k equals 1, okay? So this right here is negative 1/3. And then same thing if I just move it up 1 unit. If I move it up 1 unit, then this is going to be, if k is equal to 1, then this would be the same as making k equals negative 1/3. This is equal to, this is equal to 1/3 and so on, right? Like if I actually want to have 5, I can just copy paste this, right? Moving this down, uh, moving this down, whatever units we have to, and so on. So it'll look something like that. I only have 4. I like having 5 for no particular reason, okay? All right, perfection. I have one more example for you, which is draw a contour map of f of x y equal to root of x plus y. Same idea. Step 1, I'm going to do exactly the same thing. So step 1, I'm going to replace f of x y with k, knowing that k is a constant. So I get that k in black. I get that k it's equal to root of x plus y. Again, the way this is, it doesn't make much sense to me, but I know that y equals k minus root of x. That makes more sense to me, okay? Now, step 2, give it some values of k. So some values of k. I'm going to do what I did before, and I'll make a little table. I'm going to make a little table of values for k. Actually, y equals k minus root of x. It doesn't matter that much, right? Because I have minus x, so I'll make k 0, so that will be y equals negative x, or I do k1, then I get y is equal to 1 minus root of x, or I make k2, I get y is equal to 2 minus root of x, and then y is equal to 3 minus root of x, and then y is equal to 4 minus root of x, okay? So you have to know what the graph of negative root of x looks like. We know what, so this is step 3, graph, and we know what the graph of root of x looks like. And we also know, so this is, if this is x and this is y, we know that the root of x looks like this. Therefore, negative root of x, what we do is we flip it over the x-axis, so it looks like this. So this would be the graph when k is equal to 0, is just negative root of x. So this corresponds to to k equal to 0. Now, if k is equal to 1, I take my graph and I move it up 1 unit. So copy paste, copy paste. So this is k equals 1. So k equals 1. And then I move it up 2 units. And now I have k equals 2. So this is k equals 2. And then if I take it and I move it down 1 unit, if I take the same graph and I move it down 1 unit, even if I didn't put it in my table, this would be negative. This is negative 1, so this is k equals negative 1. And then I can even move it down 2 units, okay? So it's whatever makes more sense to you, okay? So this is negative 2 corresponds to k equals negative 2. All right, that's all I have for this section. I hope everything made sense. Bye-bye.